the final exercise here, exercise 15. We are given more than one force vector acting on the same particle, and we are supposed to calculate the magnitude of the resultant force and to represent it. Now, when we are asked about representation, we shall find the angle between the force vector of the resultant force and the x-axis. In the first step, uh, we start by projecting the force vectors that are oblique. The only one here which is oblique is f5, and the angle between f5 and y-axis is given to be 45 degrees. So applying the cosine and sine rule, cosine 45 is equal to the adjacent over the hypotenuse. The adjacent in this case is f5y, and the hypotenuse is f5 itself. And for the sine 45, it's equal to the opposite over the hypotenuse. The opposite here is equal to the x component of the force vector f5. And so we say that sine 45 is equal to fx over the hypotenuse, which is f5. So we get that fx is equal to f5 sine 45, and fy is equal to f cosine 45. Well, it won't differ because cosine 45 and sine 45 are equal, but the principle is important. Fx now, which is the x component of the resultant force. Here we have to take into consideration the positive and negative direction. The x component of f5 is to the left, so it's in the negative sense, so we have to write minus f5x. However, f1 and f2 of magnitudes 2 Newton and 5 Newton respectively are in the positive direction, so we have to write plus f1 plus f2 minus f5 sine 45 plus 2 plus 5. We get the following answer, 5.58 Newton. Just make sure that when you write sine 45 on the calculator, make sure that you have the calculator set on the degrees, not on the radians. Otherwise, you will get wrong answers. Similarly, for the y component of the resultant force, f5y and f4 are in the positive direction, f3 in the negative direction, so plus plus minus f5 cosine 45 2 Newton minus 9 in Newton, we get minus 5.58 Newton. Now, how can we get the angle between the resultant force vector? The resultant force vector in the first step could be in the first quadrant, in the second quadrant, in the third quadrant, or in the fourth quadrant. But how can we tell that? Only based on the sign of the x and y component. Since the x component is positive of the resultant force and the y component is negative, so we look in which quadrant is the x positive and the y negative. It is in this one. The first quadrant, positive x, positive y. In the second quadrant, negative x, positive y. In the third quadrant, negative x, negative y. In the fourth quadrant, positive x, negative y. So that's why we expected that the force vector to be in this quadrant. Now, how can we calculate it? If we considered an angle and we named it theta, beta, whatever, let theta be the angle between f resultant and x-axis. So now I named it theta, and as if I am moving f resultant until I reach the correct one. This is how you have to imagine it. So sine theta, if this was theta, sine theta is equal to, what is the side here, the side facing 45? It is actually fy of the resultant force, if you can imagine it. And the adjacent will be the x component. That's why we say that sine theta is equal to fy over f. And having fy and f, by f we can calculate it by using the rule radical fx squared plus fy squared, we get it. So having fy and f, we can now find sine theta, or we can use cosine theta, which is equal to fx over f, and we get the answer. Then in order to find the angle, we have to press on shift cosine, for example, 0.75 is equal to 44.9, which could be approximated to 45 degrees. So now I represented it by taking 45 degrees away from the x-axis, and I have to take into consideration its magnitude 7.89 Newton. Of course, we have to consider a certain scale here.